How's it going, guys? Today in this video, we're going to be going all over Module 11, Day 1, or 11.1, Day 1, inverses of simple quadratic and cubic functions. But it's mainly, in this video, we're mainly going to be talking about quadratics. But anyway, the function f of x equals x squared is going to be called a many-to-one function. What a many-to-one function means is that you have multiple x's that give you the same y value. For instance, f of x equals x squared. When x equals -2, you get 4, and when x equals 2, you also get 4. That means it's a many-to-one function because you have multiple x's giving you the same y value. All right? And the inverse of a quadratic function is going to be a square root function. The parent square root function is g of x equals square root of x. This is the most basic square root function we can make. The square root function is only defined for values of x to make the expression under the radical non-negative. What that basically means is that every x value underneath that square root has to be either 0 or positive. It cannot be a negative number. This is obviously, you take a square root of a negative number. We've talked about this. You get an imaginary number, and that's non-real. So we want every value underneath the square root to be either 0 or positive. Okay? So let's keep on going. So now we're going to actually talk about how to figure out our inverse, and how to graph it, and how to confirm that the inverse is actually the inverse. So what we're going to do is we're going to restrict the domain first for each quadratic function, and we're going to find its inverse. All right, so when it comes to restricting the domain, our domain of the f of x function, we want it to be greater than or equal to 0. And why we do that is because when we have, let's say it's the most basic quadratic function, just like that, the inverse is when you flip the x's and the y's. So the inverse of f of x, this function f of x is going to be like that. We switch the x's and the y's. Okay? So when you flip the x's and the y's, this new function right here in blue, that's not a function anymore. You see that we have multiple y values for one x. You can have multiple y values for x's. You cannot have multiple x's for a y. Or basically, if you don't pass the vertical line test, like we did here, you draw a vertical line. If you pass through 2 points, that function is not going to be a function. And we can see the blue graph that I drew is not a function because anytime I draw a vertical line, I'm going through more than one x value, and I can't do that. So what we're going to do to make sure that it actually works is that we're going to restrict our domain. So here we're going to be restricting it with x is greater than or equal to 0. So instead of drawing a whole quadratic, we're only going to draw half of it, one side of it. Because when you do, we end up getting a function like this. So that blue one is our f inverse, and our x is our red is our restricted f of x. So that's why we restricting the domain for x to be greater than or equal to 0. Because when we restrict it to basically half of the quadratic, when we take the inverse, it stays a function. A function has to be able to pass that vertical line test we talked about in blue, because if it doesn't pass it, it's not going to be a real function. And I know this is probably a lot. If it's confusing you, just remember that what we're going to do is we're always going to restrict any quadratic function to be greater than or equal to 0. If that's a little confusing, just think of it that way. We're going to restrict the domain of the function, of a quadratic function anyway, to be greater than or equal to 0. That way, the inverse is also a function. So we're always going to restrict it like that. All right? So now what we're going to do is we're going to find the inverse. To find the inverse, it's relatively straightforward. So what we're going to do is we're going to rewrite this f of x equals 0.5 times x squared into y equals 0.5x squared. Just change f of x for y. And once we get to this point, what we're going to do is we're going to flip the x's and the y's. So instead of y equals, we'll have x equals 0.5 y squared. There's no real math in this. We just flip where the x's and the y's are. And once we do that, we're just going to solve for y again. So we multiply by 2 on both sides to get rid of that 0.5. 2 times 0.5 is just 1, so we can get rid of it. 2x equals y squared. Take the square root of both sides. We get that the square root of 2x equals y. And we can change that y now into an f inverse of x, because that's what we just solved for. So the inverse function of x equals the square root of 2x. So to find your inverse, flip where your x and y's are, solve for y again, and then just change y for this f inverse of x. And that right there is our inverse function. Okay? So now that we found our inverse, what we're going to do now is we're going to figure out what our domain is going to be. Remember, everything underneath the square root of anything underneath the square root has to be greater than or equal to 0. That way, we can actually have real numbers, not have imaginary numbers. So what we're saying is that everything underneath the square root, that 2x, has to be greater than or equal to 0. Or we can divide by 2 on both sides and just simplify 2x has to be greater than or equal to 0, not 2. 0 divided by 2 is 0. And that's exactly what our domain is going to be. X has to be greater than or equal to 0. All right, so we figured out our domain. And now what we're going to do is we're going to confirm that the inverse we found is actually our inverse. And we do that by using these two formulas. They look a little confusing, so we're going to go through it step by step. So this first function that we have over here, that's f inverse in terms of f of x. And what that means is we're going to write this first function, the f inverse function, which we found to be the square root of 2x. We're going to rewrite that in terms of f of x. Or in other words, we're going to replace the x in our f inverse function right there to our function f of x. So we have the square root of 2, and we're going to write it, our x, in terms of f of x. So we said our f of x, we double check, is 0.5 x squared. So instead of x, we're putting 0.5 x squared. So that's what that means. We're writing the inverse function in terms of f of x. So we have our function like this now, and we're just going to go ahead and solve it out. 2 times 0.5 is just 1. 0.5 is the same as 1/2. 2 times 1/2 is 1. So we're left with the square root of x squared, and the square root of x squared is x. And I forgot to say this in the beginning, but we want both of these equations to equal x. Sorry about that, but we're going to solve both of these equations, both of these compositions, and they both need to equal x to confirm that our function is truly a function. So we solved the first one out, we got x. That's exactly what we wanted, so we got it. Next, we're going to do the same thing with f of f inverse of x. So again, we have this f function over here, and we're going to put it in terms of the inverse. Or in other words, we're going to rewrite our f of x function, which is 0.5 x squared. And we're going to replace the x value with our f of x right there. So we end up getting 0.5. Instead of our x value, we put our f inverse function, which is the square root of 2x, all raised to that square. We still bring down the exponent. That's not a variable, so we keep it there. So it becomes 0.5 times the square root of 2x, all squared. So now we're going to solve this out. So the square root of, square root of 2x raised to the second power, that square root and that square function, they cancel each other out. So we're left with 0.5 times 2x. Oh, sorry about that. 0.5 times 2 is going to be 1. So we're left with x. And that's exactly what we wanted. We got both functions, both compositions to equal x. So that proves that our inverse function is truly an inverse. All right, we'll go over another problem of this on the next slide. So it doesn't make too much sense. We're going to have another problem to go over it. Okay? And now the last thing we need to do is we need to graph our f of x and f inverse function. So how we're going to do that is we're really just going to graph the f of x function. So we'll make a table, x and y's. And what we're going to do is we're going to pick some x values. We only have 0, 1, 2, and 3 here. So that's what we'll use, 0, 1, 2, and 3. And we're going to plug these into our f of x function that we had from the beginning, and that gives us our point for our graph. We plug in 0 into this equation, we end up getting 0. 0 squared is 0, and 0 times 0.5 is going to be 0. We plug in 1, 1 squared is 1, 1 times 0.5 is 1 half. We put in 2, you get 2, and when you put in 3, you get 4.5. So that's our f of x function. So let's go ahead and graph that. We have 0, 0, 1, 1 half, 2, 2, and 3, 4.5 will be way up there somewhere. So we're going to graph this, and it looks exactly how we planned it to look. It's going to look like a like half a quadratic. We restricted the domain to be greater than or equal to 0. That's why we started with 0, because we're restricting the domain of f of x to be greater than or equal to 0. And it looks exactly how we expected it to look, which would be half a quadratic. And now for our f inverse function, all we're going to do is we're going to take our values on our table, on our f of x table, the one in red, and we're just going to flip it. So for the first point, we have 0, 0. We flip it, it's going to say 0, 0. Now for 1, 1 half, we flip that into 1 half 1. 2, 2 is the same numbers, they stay the same. And then for 3, 4.5, that becomes 4.53. For the inverse, all we do is switch the x and y values. So we're going to do the same thing for the table. We just switch the x and y terms, and that gives you your f inverse function, or your f inverse table. So we're going to graph this too. We have 0, 0, 1 half 1, 2, 2, and 4.53 will be something probably around right there. And it's going to look like that. And that's what our function is going to look like. Okay? And something else to kind of note is that how we reflect, or how we figure out our inverse function, is that we just reflect it over this y equals x line right here. That's not perfect, but we have a y equals x line, and how you get your inverse function is you reflect it across that line. Okay? So that is number one. There's a lot to take in. If you need to rewatch it, please do. But for now, we're going to go on to number 2 and do another problem very similar to this. Okay? So first thing we're being asked is to restrict the domain. Like we said before, it's a quadratic, so we're always going to restrict it to x is greater than or equal to 0 in our case. Okay? That looks like a 3. It shouldn't be. Okay? So now that we restricted our domain to be every x value greater than 0, greater than or equal to 0, we're going to find our inverse. So we're going to rewrite our function, y equals x squared minus 1. We flip the x's and the y's, so we get x equals y squared minus 1. We're going to solve for y. X plus 1 equals y squared. Take the square root of both sides. We get square root of x plus 1 equals y, or the f inverse of x equals the square root of x plus 1. Switch to x and y terms, solve for y again. That's your inverse function. So we found our inverse function. Let's figure out our domain of the function. So we have, underneath the square root, we have x plus 1. And we want every term in there to be greater than or equal to 0. So x has to be greater than or equal to negative 1. We cannot be anything less than 0. We can equal 0. So our domain will be x is greater than or equal to negative 1. So we have our domain, we have our inverses, and now we're going to confirm by composition. So we're going to use our two same formulas. Let's actually do this down here to give ourselves a little more room. So we have the f function of the f inverse, and we also have the f inverse function of f of x. All right, so that's what we're going to be solving for. We need both of these to equal x. So let's do the first one first. The function in term, the f of x function in terms of f inverse. So we have the function f of x. which we said was, double check, x squared minus 1. So we have x squared minus 1 as our function, but we're going to replace every x here with our f of x function right there. So x squared becomes our inverse function, which is the square root of x plus 1, all squared, minus 1. So we're going to solve this out now. The square root of x plus 1 all squared gives us x plus 1. The square root and the square cancel out. We have x plus 1 minus 1. X plus 1 minus 1, these cancel out to leave us with x, which is exactly what we wanted. Now for the f inverse of f of x, we have the inverse function, which we said was the square root of x plus 1. And now we're going to replace every x with our f of x. So the x, that's going to change into our f of x function, which we said was x squared minus 1. Forgot it for a second, but that's what it is. X squared minus 1 plus 1. So that's what we have, and this is what we're going to solve out. Right? We replace the x with our f of x function, and when we solve this out, we end up getting the square root of x squared, or just x. The square root of x squared is just x, and that's what we got. So both functions ended up equaling x. That means we got the right inverse function. And that is also an inverse. So we checked with composition. So now all that's left is to graph f of x and the f inverse of x. So we're going to do it the same way we did before. We're going to make a table of f of x. So on this table, we're not going to go through all of those. We're really just going to go with 0, 2, and let's do 3. Okay? So when you plug in 0, we get 0 squared minus 1. That's going to be negative 1. We plug in 2. 2 squared is 4. 4 minus 1 is 3. Plug in 3. We get 3 squared, which is 9. 9 minus 1 is 8. And something I want to kind of point out again is that when we're making our f of x table, we cannot use any x value less than 0. And that's because we restricted our domain so that our f of x function is every x value greater than or equal to 0. So I just want to double check, not double check, but remind you guys that we cannot use any x value less than 0 in our f of x table. All right, so we start at 0 and we go up from there. So that's our table for f of x. Let's go ahead and graph it. We have 0, negative 1, 2, 3, and 3, 8. So it's a very steep half of a quadratic, which is exactly what we wanted. And now for our f of x, or sorry, our f inverse function, all we're going to do is flip our x's and our y's from our f of x table. So we have 0, negative 1 for our first point for our f of x table. That now becomes negative 1, 0. 2, 3 becomes 3, 2. And 3, 8 becomes 8, 3. Just flip the x's and the y's. So for our f inverse, we get negative 1, 0. It'll be right there. 3, 2. And 8, 3. So we get a very steep square root function. And we can see here that we are indeed being reflected across that y equals x line, which is what makes an inverse. That's how you get an inverse. You reflect the graph over the y equals x line. Okay? So that's number 2. I want you guys to do number 3 on your own, and then in a second I'll post the answer to that, and we'll go over it. But for now, pause the video and try doing that one on your own. Okay, so here's the answer to number 3. When we restrict the domain, like we said before, we're just going to leave it as x is greater than x such that x is greater than or equal to 0. After that, we're going to find our inverses. So to find our inverse, we're going to rewrite our equation as y equals. We're going to flip the x's and the y's. So we end up getting x equals 3y squared instead of y equals 3x squared. Then we solve for y again. When we do, we should get this f inverse of x equals the square root of x all over 3. Once we do that, We're going to figure out our domain. We're just going to set everything underneath the square root to be greater than or equal to 0, like I did right here. So we get that x is greater than x over 3, sorry, is greater than or equal to 0, multiplied by 3 on both sides, and we get that x is greater than or equal to 0. And that's what our domain is going to be. Next, we're going to do our compositions. We're going to double check our answer, our inverse. So we have f in terms of f inverse of x, that should equal x. So our function of x is 3x squared. We replace the x with our inverse, which is the square root of x over 3. When we did that, we get 3 times the square root of x over 3, all squared. When we solve that out, the square root of x over 3 to the second power, the square root and the square cancel each other out. We're left with 3 times x over 3, which gives us x. Now for our other part of our composition, we get the f inverse. In terms of f of x should equal x. Our inverse function was the square root of x over 3. We replace the x with our regular function, which is 3x squared. So we have the square root of 3x squared all over 3. We can actually make this a little more clear, because we're taking the square root of everything, top and bottom. So it's a square root of 3x squared all over 3. The 3's cancel. We're left with the square root of x squared. And the square root of x squared is just x. Both parts of the composition are x. They both need to equal x for our composition to be true. And they do, so our composition checks out. We're good to go. Our inverse is actually our inverse. Next, we're going to graph our f of x and f inverse of x. So we make our f of x table. We add it with 0, 1, and 2. We end up getting the points 0, 0, 1, 3, 2, 12. And when you get your inverse function, you flip your x's and your y's. 0, 0 is going to stay 0, 0. It's the same number. 1, 3 becomes 3, 1. And 2, 12 becomes, I put 12, 1, but that should be 12, 2. There we go. So that's what our f inverse table should look like and what our f of x table should look like. And when we graph it, we get something like this, where we can see that the functions are indeed being reflected over the y of x line. It's not perfect. I'm not a great artist, but it is being reflected over the y of x line, which is what an inverse is doing. All right. So that's number 3. So we're going to go on to the word problems. Over here, we're going to be figuring out the inverse of a quadratic model. So quadratic functions are used to model real-world applications. It's often useful to find and interpret the inverse of a model. When working with real-world applications, it's more useful to write x of y for the inverse of y of x. And we're going to see why we're going to do that in this next word problem. So we're going to find the inverse of each quadratic function in numbers 1, 2, and 3. So for number 1, we're told the function d of t equals 16t squared, gives the distance d in feet that a dropped object falls in t seconds. So that d of t equals 16t squared is saying the distance in terms of time is going to give us 16t squared. In other words, the distance that it takes for an object to drop is going to take t seconds. That's how you find the distance, by plugging in your time that it takes to drop. But what we're going to do is we're going to rewrite this function to be t of d. And we're going to do that so we can find the time it takes for an object to fall in X amount of feet. So we keep on reading. We're told to find the time in t seconds it takes for an object to fall a distance of d feet. That's what t of d equals. So then we're going to estimate how long it will take for a penny dropped into a well to fall 48 feet. So that's ultimately what we're going to be solving for. So that's a lot to take in. So let's kind of break it down step by step. So the very first thing we're going to do is we're going to rewrite d of t as just d. So the distance is going to equal 16 times time squared. Next, we're going to solve for t, because we're ultimately being asked how long does it take. We're asking how long it will take for a penny to be dropped into a well that's 48 feet. So we know the distance, but we need to figure out what our t is going to be. So that's why we're going to resolve it for t equals. So we're going to divide by 16 on both sides. We get d over 16 equals t squared. Take the square root, and we get that t equals the square root of d over 16. So that's what t equals. That's how we figure out what our time is going to be when we're given our distance. So we're going to write t as t of d. So just all that means is that we have our time in terms of the distance. And that equals the square root of d over 16. So we have our t of d function. And now what we're going to do is we're going to figure out what the question is ultimately asking us for. We're asking how long it'll take for a penny that was dropped into a well to fall 48 feet. So we don't know what our time is. That's what we're solving for. But we do know that our distance is 48. So we want t in terms of 48, which will equal the square root of 48 over 16. Just plug in 48 for d. Okay? So now we're going to simplify this out. So this t is going to equal the square root of 48 over 16. 48 divided by 16 is just 3. And the square root of 3 is, I believe, about 1.73. Equal to, it's approximately 1.73. And we're usually just going to round to the second decimal place. We're asking you to estimate. Sorry. So that's how you do a word problem. So let's keep on going to number 2. We'll work that one out together, and then I'll have you guys do number 3 on your own, and we'll double check your work. So for number 2, we're told the function e of v equals 4v squared. And that gives the kinetic energy E in joules of an 8 kilogram object that's traveling at a velocity of v meters per second. So basically, this E is the energy it takes for something to go at a certain velocity v. Okay? So what we're going to be doing is that we're going to resolve this to figure out the velocity, so we can figure out the velocity, or how fast something's going, how much energy it takes. And once we do that, we're going to figure out the velocity required to have a kinetic energy of 60 joules. So ultimately what we're doing is we're solving for v of E, or v equals, and then we're going to be plugging in 60 for E to solve for our v. So we're going to solve this out. We have E equals 4v squared divided by 4. E divided by 4 equals v squared. Take the square root of both sides. We get the square root of E all over 4 equals the square root of v squared is just v. Or in other words, v of E equals the square root of E all over 4. That's our v of E function, or our v equals. And now we're going to use this to figure out what v will be when E is 60. We're told we want to know the velocity required for an 8 kilogram object to have a kinetic energy of 60 joules. Or basically, what's v going to be when E is 60? So we want v of 60 will equal the square root of 60 over 4. 60 divided by 4 is 15. So we want the square root of 15, which is approximately 3.87. Okay? So that's your v. So we have one more problem. I want you guys to pause the video and try that out on your own. Okay? So this is what you should have gone for number 3. So we have the function a of r equals pi r squared. And we're going to solve this for r now, for r of a. So you solve it out. You should have gotten r of a will equal the square root of a all over pi. So what we want now is we want to know what the radius is going to be when we have an area of 40 centimeters squared. So we have r of 40 equals the square root of 40 over pi. Pi is approximately 3.14, so that's what we're going to use. So this really should say r is approximately 40 over square root of 40 over 3.14. So square root of 40 divided by 3.14 is 12.74. So r will be approximately the square root of 12.74, and the square root of 12.74 is approximately 3.57. So the radius of an object with an area of 40 centimeters squared will be approximately 3.57. That's the last of the notes. Hopefully that helped, guys. That's about it.